Hello, wherever you are right now, whatever time it is. I hope you're warm, still, and ready to rest. You're here with HypnoScience, where real science is told slowly, softly, and without urgency. Tonight, we'll explore something you've seen countless times, but may never have fully named or understood. We'll be going through all the types of clouds, how they're classified, what they look like, and the calm, unhurried processes that cause them to appear. There are no stories here, no mysteries, just water vapor, air pressure, temperature gradients, and the steady movement of invisible forces. Let's begin with the basic structure of cloud classification. Clouds are divided into 3 altitude levels based on where they form in the atmosphere: high-level clouds, mid-level clouds, low-level clouds. High-level clouds form above 20,000 feet. They are made mostly of ice crystals. These include cirrus, cirrostratus, and cirrocumulus. Mid-level clouds form between 6,500 and 20,000 feet. They may be made of water, ice, or both. These include altostratus and altocumulus. Low-level clouds form from the surface up to 6,500 feet. They are mostly made of water droplets. These include stratus, stratocumulus, and nimbostratus. There are also clouds that span more than one level. These are called vertically developed clouds. Now we'll go through each type, slowly, one at a time. Cirrus clouds. These are high clouds. They appear thin, wispy, and feather-like. They are made of ice crystals. They form in cold air where water cannot remain liquid. They stretch across the sky, often pulled by strong winds. They do not bring rain, but they may signal a change in the weather. The name cirrus comes from Latin. It means curl of hair. Cirrostratus clouds, also high clouds. They form a thin, transparent sheet across the sky, made of ice crystals. They may create a halo around the sun or moon. This is caused by light bending through the crystals. Cirrostratus clouds often arrive before a warm front. They may lead to rain within a day, but they are not storm clouds. Cirrocumulus clouds. Small white patches. They look like grains of rice or fish scales, sometimes called mackerel sky. They are also high clouds, made of ice crystals. They do not bring rain, but may suggest instability in the upper atmosphere. Altostratus clouds. These are mid-level clouds. They appear as a uniform gray or blue-gray sheet, thicker than cirrostratus. The sun may still be seen through them as a dim circle. They often form ahead of a warm front. They may bring steady rain or snow. Altocumulus clouds, also mid-level. They appear as white or gray clumps, larger than cirrocumulus. They may form lines or patches. If seen on a warm morning, they may signal afternoon storms, but they do not produce rain themselves. Stratus clouds. These are low-level clouds. They form a gray, featureless blanket across the sky. They may cover large areas, often mistaken for fog, though they hover slightly higher. They bring drizzle, mist, or nothing at all. Stratocumulus clouds. Low, lumpy, gray clouds. They may have breaks of blue sky, often seen after storms. Heavy but usually dry. They move slowly. They do not produce significant rain. Nimbostratus clouds. These are rain clouds. Low and thick. Dark gray. They bring steady precipitation. Snow or rain, often lasting for hours. They have no clear shape, just density and stillness. These are the basic types of layered and patchy clouds. In the next segment, we'll continue with vertical clouds, cumulus, cumulonimbus, and others with height and motion. For now, let your thoughts slow. Let the clouds drift through you. Nothing urgent. Only vapor. Only rest. Nimbostratus clouds bring long, steady rain. But not all clouds are content to spread. Some rise. These are vertically developed clouds. They begin low and grow tall, formed by heat, lifted by rising air, shaped by instability. The most familiar of these is the cumulus cloud. The name means heap. These clouds are puffy, rounded, and white. They have flat bases and cauliflower-shaped tops. They form on sunny days, when warm air near the surface rises. As the air lifts, it cools. Moisture condenses. A cloud begins to build. Cumulus clouds are made of water droplets. Their bases often hang just above the ground. They drift slowly. Some dissolve within hours. Some continue to rise. When one keeps growing upward, it becomes cumulonimbus. The thunderstorm cloud. Dark at the base, bright at the top, towering tens of thousands of feet into the sky. Its top flattens into an anvil shape. This marks the top of the troposphere, where rising stops. Inside the cloud, the air moves quickly. Updrafts lift moisture. Downdrafts carry rain and hail. Electric charges form. Lightning flashes. Thunder follows. And sometimes wind or tornadoes below. Not every cumulonimbus becomes violent. Some bring a short downpour and fade. They are most common in the heat of day. In summer, over land. There are also clouds shaped by special conditions. Lenticular clouds form over mountains. Smooth, layered, stationary. They appear when moist air flows up and over a peak. The air condenses in waves. Each wave holds a disc-shaped cloud in place. They do not move, even when the wind is strong. Mammatus clouds form beneath larger cloud masses. Pouches of moisture hang like soft bulges. They indicate motion within the air. Vertical turbulence, often seen beneath the anvils of thunderstorms. They look heavy, but they fall slowly and do not bring rain. Pileus clouds appear as thin caps, resting on top of strong updrafts. When a cumulus grows fast, it pushes into cooler, moist air above. The air condenses quickly, and a smooth lid forms. It does not last long. The cloud beneath overtakes it, but for a moment it is there, floating, still. Fog is also a cloud, but it touches the ground. It forms when surface air cools to its dew point. Moisture condenses. Tiny droplets hang in the air, reducing visibility. It is common in valleys, near lakes, after sunset, and before dawn. Fog does not rise. It settles. It moves slowly, often silent. There are artificial clouds as well. Contrails, short for condensation trails. They form behind jet engines. Exhaust gases meet cold air. Water vapor condenses, freezes, forms a trail. Some fade quickly. Some linger. They spread, resemble cirrus clouds, but form differently. The physics is the same. Clouds come in many forms. Flat, tall, smooth, jagged. Each one made from the same thing. Water vapor. Lift. Cool air. No cloud is permanent. They grow. They decay. They vanish. Nothing holds them in place. Above us, clouds are always forming, always ending, without pause, without urgency, just motion, just vapor, just time. Clouds do not appear by chance. They form because certain conditions are met. Always the same elements, always the same rules. Air must rise. It must cool. It must reach saturation. Only then does water condense. Only then does a cloud begin. Rising air cools at a steady rate, roughly 9.8 degrees Celsius per kilometer. This is called the dry adiabatic lapse rate. If the air reaches its dew point, water vapor condenses. Tiny droplets form, billions of them, each one clinging to a microscopic particle. Dust, salt, smoke. These are called condensation nuclei. The droplets are light, too small to fall. They remain suspended, drifting, joining, reflecting light. There are four main ways air is lifted. The first is convection. The sun heats the surface. The surface heats the air above it. Warm air rises. Cool air sinks. This forms thermals, vertical columns of air. Clouds form at the top of these currents, usually cumulus, sometimes more. The second is orographic lifting. Air meets a mountain. It cannot go through, so it goes up. As it rises, it cools. Clouds form along slopes. Winds continue to push moisture over peaks. Rain often falls on the windward side. The leeward side is dry. This is called a rain shadow. The third is frontal lifting. Two air masses meet, warm and cold. Warm air is lighter. It is forced upward over cold air. At the boundary, called a front, clouds appear. In warm fronts, the lift is gradual. Altostratus, nimbostratus. Steady rain. In cold fronts, the lift is rapid. Cumulonimbus. Thunderstorms. The fourth is convergence. Air moves from different directions toward the same point. It has nowhere to go but up. It rises, cools, condenses. This often occurs near the equator and along low-pressure systems. Each lifting mechanism is slow, predictable, a chain of causes, each one tied to physics. Once air is rising and saturated, a cloud will grow, but not always for long. Clouds are fragile. They depend on temperature, moisture, and motion. Change one of those, and the cloud begins to dissipate. This happens in a few ways. If air descends, it compresses. Compression heats the air. The relative humidity drops. Water droplets evaporate. The cloud fades. If drier air mixes in from the sides, evaporation increases. This is called entrainment. It breaks up cloud edges, thins the mass, reduces height. If sunlight returns, the surface warms. Stability increases. Rising air slows. The cloud no longer builds. Even when clouds seem still, they are always changing. Evaporating on one side, forming on another. Every second. A cloud is not a single object. It is a process, a balance of creation and decay. Sometimes evaporation can be seen as wisps falling below the cloud base. This is called virga, rain that never reaches the ground, falling through dry air, turning to vapor before it lands. Cloud formation and dissipation are part of the water cycle, one stage among many. Evaporation, condensate, ion, precipitation, runoff, and again. Clouds are temporary structures, but their behavior follows permanent laws. The balance of temperature and pressure, the shape of the land, the movement of the wind. Every element plays a role, and all of it, quiet, continuous, unaffected by human urgency. The next time a cloud drifts overhead, it may be growing, or it may be disappearing. Most of the time, both are happening at once. This quiet cycle has no center, no climax, only motion, only change. Clouds do not always hold their moisture. Sometimes they let it go. This release is called precipitation. It takes many forms: rain, snow, hail, sleet. Each begins the same way, with a droplet or a crystal formed high in the cloud. But not all clouds produce precipitation. The droplets must grow, must become heavy enough to fall, must overcome the resistance of the air, and must survive the journey to the ground. There are two main processes that lead to this. The first is called the collision coalescence process. It occurs in warm clouds, mostly in the tropics. Cloud droplets vary in size. Larger ones fall faster. They collide with smaller ones. They merge. The new drop is heavier. It falls faster. It collects more. And eventually, it becomes a raindrop. This process depends on instability, on vertical motion, on moisture content. It happens invisibly, but constantly. The second process is the Bergeron-Findeisen process. It occurs in cold clouds, where both ice crystals and water droplets coexist. Ice has a lower vapor pressure. Water vapor moves toward it. Ice crystals grow. Droplets shrink. The ice becomes heavy. It falls, sometimes as snow, sometimes melting into rain, depending on the temperature below. This process dominates in mid-latitude regions. It explains why snow can fall even when clouds are not thick, because ice grows quickly, quietly, in thin, cold air. Once particles fall, they are called hydrometeors. Rain is liquid water, usually at least 0.5 millimeters in diameter. Smaller droplets are called drizzle. Snow is made of ice crystals, grouped in hexagonal shapes. Their patterns depend on temperature and humidity, each one different, but following physical laws. Hail is formed in cumulonimbus clouds. Updrafts lift particles upward again and again. Each time, more water freezes around the core. The hailstone grows. When it is too heavy for the air to support, it falls. Sleet is frozen rain. Raindrops pass through a layer of freezing air near the surface. They solidify before hitting the ground. The result is hard pellets. Freezing rain is different. The drop remains liquid in the air, but freezes on contact with a cold surface, creating ice. Smooth, coating, dangerous. The kind of precipitation depends entirely on the vertical profile of the atmosphere, not just the surface temperature, but each layer, top to bottom. Cool air above warm, warm below cold. Each combination makes a different result. Sometimes rain begins but never finishes. It falls, then evaporates. This is virga. It appears as streaks below the cloud, fading into dry air, never reaching the ground. Common in deserts or at altitude. In other cases, precipitation reaches the ground, but not as water. It mixes with dust, with ash, with pollution, creating dry, grainy residue. In places like the Middle East, China, or the American Southwest, it may leave reddish stains on the surface. Most rain begins high, 5,000 feet, 10,000, even higher. The journey down takes time, seconds, but each one matters. Drops are shaped by the air they pass through. They may be spherical, flattened, or broken apart. Most raindrops are small. Larger ones fall faster, but break apart at a certain size, around 6 millimeters, no larger. Precipitation is the end of the cloud's life, or part of its cycle, because the rain may fall, but the cloud may continue. Water reaches the ground, runs over land, soaks into soil, evaporates again, returns to the air, and forms a cloud once more. It is not a circle. It is a spiral. Long, slow, ongoing, from vapor to droplet, to crystal, to fall, and rise again. No rush, no noise, only process, only balance. Clouds have been named and classified for over 2 centuries. Not just observed, but recorded, compared, sorted. The first system of cloud classification still used today was created in the early 1800s by Luke Howard, an amateur meteorologist, a chemist. He proposed a system of Latin-based names, descriptive, simple, repeatable. That system has expanded, but the core remains. Cloud names are made from combinations of 4 base terms. Cumulus meaning heap or pile, used for clouds with vertical growth. Stratus meaning layer, used for flat, spread out clouds. Cirrus meaning curl or fiber, used for high altitude, wispy clouds. Nimbus meaning rain. Said to describe precipitation-bearing clouds. Additional prefixes and suffixes are applied to adjust meaning. Alto indicates mid-level clouds, found between 6,500 and 20,000 feet. Alto stratus, alto cumulus. Cirro indicates high clouds, above 20,000 feet. Cirrostratus, cirrocumulus. Nimbus is used for rain. Nimbostratus, cumulonimbus. Each name is a combination of form, height, and function. No cloud has a unique name. Only descriptive terms. Grouped, compared. In total, the World Meteorological Organization, or WMO, recognizes 10 main cloud genera. They are cirrus, cirrostratus, cirrocumulus, altostratus, altocumulus, stratus, stratocumulus, nimbostratus, cumulus, cumulonimbus. Each of these has subcategories based on size, transparency, pattern, and special features. These are called species and varieties. For example, cumulus humilis, small, flattened cumulus clouds. Cumulus congestus, taller, growing cumulus clouds. Stratocumulus stratiformis, spread out in layers. Stratocumulus castellanus, with turreted tops. Varieties describe how the cloud appears. Translucidus allows sunlight or moonlight to pass through. Opacus blocks light. Undulatus, wavy or rippled. Radiatus, in parallel rows. Clouds may also include accessory features. Pileus, the cap cloud, briefly atop a rising column. Velum, a thin veil beneath the main cloud. Virga, visible precipitation that evaporates before reaching the ground. Precipitatio, precipitation that does reach the ground. Mamma, the pouch-like structure under mammatus clouds. Each feature is noted for scientific observation. Each cloud may include multiple classifications at once. For example, altocumulus stratiformis translucidus undulatus. These terms may appear complex, but they describe only what is seen. Shape, layering, light, motion, altitude. No interpretation, only description. The WMO has maintained the International Cloud Atlas since 1896. The latest edition was released in 2017. It includes standardized photographs, terminology, guidelines for observation. It is used worldwide by scientists, pilots, educators, and weather services. Cloud observation follows simple steps. Determine cloud type. Estimate coverage. Measure altitude when possible. Note motion. Precipitation. Transparency. In aviation, cloud levels are noted in octas. An octa equals 1/8 of the sky. Clear sky is 0 octas. Overcast is 8. This system helps describe how much of the sky is covered. Low clouds are significant for visibility. Mid-level clouds indicate moisture and trends. High clouds signal changes in upper atmosphere. All of it contributes to forecasting, but the classification remains unchanged, still based on form, height, and pattern. The naming system does not require judgment. It does not change with mood or language, only with what is seen. A stratus cloud over Siberia is the same as a stratus cloud over Peru. Shape, altitude, light, that is all. Cloud classification is not artistic. It is structural, consistent, a system for observing what the sky holds, without interpretation. No symbols, no predictions, only names, given slowly, repeated, recorded. Clouds are not only visual, they are thermodynamic. They play a key role in regulating Earth's temperature at both local and global scales. They affect the planet's radiation budget, the balance between incoming solar energy and outgoing infrared radiation. This balance is delicate, continuous, and clouds influence it in two main ways. First, clouds reflect sunlight. This is called albedo. The term means whiteness. It is the fraction of solar energy that is reflected by a surface. Bright clouds like stratocumulus reflect more light. Thick layers can reflect up to 90% of incoming radiation. When clouds reflect sunlight, less energy reaches Earth's surface. This has a cooling effect. Daytime temperatures may be lower. Photosynthesis may slow. Evaporation may decrease. Second, clouds trap infrared radiation. This is known as the greenhouse effect. Earth emits heat energy, mostly in the form of long-wave radiation. Clouds absorb some of this energy. They re-emit it in all directions, including downward. This keeps surface temperatures from falling too quickly, especially at night. Different types of clouds have different effects. High, thin clouds like cirrus trap heat more than they reflect sunlight. This produces a net warming effect. Low, thick clouds like stratus reflect more sunlight than they trap heat. This produces a net cooling effect. Mid-level clouds may do both, depending on their thickness, coverage, and water content. The total effect depends on cloud type, location, season, and time of day. Clouds also influence precipitation patterns, which affects vegetation, surface albedo, carbon uptake, and water availability. In the tropics, deep cumulonimbus clouds transport heat upward. They release latent heat as water condenses. This drives atmospheric circulation, forming cells of rising and sinking air, known as Hadley cells. These patterns define wind belts and rain belts, which shape deserts, forests, and monsoons. In polar regions, clouds help retain warmth. Even thin cloud layers prevent surface radiation from escaping freely. This maintains higher night temperatures, delays surface ice formation, and slows radiative cooling. Clouds are also involved in feedback loops. As temperatures rise, more water evaporates. More evaporation leads to more clouds. More clouds may reflect more sunlight, a negative feedback. But some clouds may trap more heat, a positive feedback. The net effect is uncertain. Models vary. Observations continue. Satellites monitor cloud coverage daily, using instruments like MODIS and Ceres. They track cloud height, optical thickness, droplet size, and radiative properties. Climate models include cloud physics, but cloud behavior remains a major source of uncertainty, especially for future projections. Due to complex interactions between cloud type, altitude, aerosols, and warming trends. Aerosols affect cloud formation. They serve as condensation nuclei. More aerosols may mean more but smaller droplets. This increases cloud brightness, which can enhance albedo and reduce rainfall. This is called the aerosol indirect effect. Volcanic eruptions can inject aerosols into the stratosphere, creating high clouds. These reflect sunlight, lower temperatures, and influence global weather. For months, sometimes years, even human activity alters cloud cover. Urban areas produce heat and particles. Ships leave trails of clouds across oceans. Aircraft affect cirrus formation. All of it contributes. Clouds are not passive. They do not just appear. They respond, and they shape. They insulate. They cool. They redistribute heat. Clouds are the largest source of uncertainty in climate sensitivity because their dual role, reflecting and insulating, makes them complex. They are made of water, but they carry energy. Visible, but analytical. Soft, but essential. Clouds are temporary. They form. They grow. They fade. Then vanish. Each one has a lifespan, defined by structure, environment, and motion. Some last only minutes, others hours. Few persist for days, but all of them end. The average cumulus cloud lasts less than an hour, formed by surface heating, built by rising air. When the heat source weakens, or the surrounding air stabilizes, the cloud dissipates. Straightest clouds may last longer. They form in stable air, with little vertical motion. They spread, linger, sometimes for an entire day. They fade slowly, as air dries, or as wind moves them apart. Cumulonimbus clouds build rapidly and collapse quickly. They rise in unstable air, fueled by warm surfaces. Once the updraft weakens, or the moisture is exhausted, the system collapses. Downdrafts dominate. Precipitation ends. Cold air spreads at the surface, suppressing further lift. This process may take 2 to 3 hours, though shorter events are common. Cirrus clouds form at high altitudes, in dry, thin air. They can persist for hours, drifting slowly. They do not change quickly, but they also do not remain indefinitely. Upper-level winds stretch them, thin them, mix them with other clouds, until they fade. The formation and dissipation of clouds is controlled by stability. Stability refers to the atmosphere's resistance to vertical motion. In stable air, lifted parcels cool quickly. They become denser than surrounding air and sink. In unstable air, lifted parcels remain warmer. They keep rising, and clouds grow as stability increases. By surface cooling or upper-level warming, existing clouds shrink. Air also loses moisture through mixing, through precipitation, through warming. When evaporation exceeds condensation, cloud droplets vanish. The cloud becomes transparent, then invisible. This can be observed at cloud edges, where turbulence mixes dry and moist air, called entrainment. It erodes cloud boundaries, limits vertical growth, speeds dissipation. Strong downdrafts can also destroy clouds. Falling air warms as it descends. This inhibits further lifting and dries the cloud base. Wind shear, a change in wind speed or direction with height, can tear clouds apart, especially vertically developed clouds. Tops may drift one way, bases another. The structure weakens and collapses. Clouds also change when they merge. Two small cumulus clouds may join, forming a larger cloud with stronger lift, more potential for precipitation, or they may shade the surface below, cooling it, reducing the heat that drives their own growth. A self-limiting process, common in scattered afternoon convection. Some clouds disappear without motion, slowly evaporating in place, leaving no trace, only dry air and sunlight. Others vanish in transition, reforming as a different type, cumulus flattening into stratus, altostratus fading into cirrostratus. The change is not dramatic, only structural. Cloud lifespans are rarely documented in exact terms, because no two clouds are identical. Their development is continuous, not binary, not on or off, only forming and ceasing. Clouds do not die, they resolve. Water returns to vapor, invisible, waiting for the next cycle, the next lift, the next layer. Cloud evolution is often symmetrical. A period of growth, a period of decline. Even the tallest towers fall. Radar can observe this. So can satellites. Time-lapse imagery reveals cloud life clearly. Formation, expansion, disruption, and disappearance. It is a system of balance, of small forces, of energy spread across thousands of meters, reacting to temperature gradients and invisible boundaries. There is no conclusion, only continuation. Moisture moves. It becomes cloud, then not. Repeated endlessly. Not all clouds form naturally. Some are influenced by human activity, by design, by experiment, through processes known as weather modification. The most common method is cloud seeding, a technique developed in the 1940s. Still in use, still studied. Cloud seeding attempts to enhance precipitation, or suppress hail, or disperse fog. It involves introducing particles into the cloud to encourage condensation or ice formation. The particles used are called nuclei. They act as centers around which water vapor condenses. or freezes. Typical materials include silver iodide, a compound with a crystalline structure similar to ice. Potassium iodide, also used in similar applications. Dry ice, solid carbon dioxide, which cools air and induces freezing. Salt particles, used especially in warm clouds to increase droplet size. These materials are released into clouds by aircraft or by ground-based generators. They are carried upward by winds, distributed through updrafts. The goal is to create more and larger precipitation particles, to trigger rainfall sooner, or in greater quantity, or to limit hailstone growth by initiating earlier freezing. Cloud seeding requires precise conditions, sufficient moisture, proper temperature ranges, and the presence of clouds already capable of development. It does not create clouds from clear skies. It modifies existing clouds through nucleation. Results vary. Precipitation increases are typically small, often between 5 and 15%. Difficult to measure, difficult to isolate from natural variability. Hail suppression programs also use seeding. The goal is not to eliminate hail, but to reduce the size of hailstones by increasing the number of ice particles. Smaller hailstones cause less damage. This method is used in agriculture-heavy regions, with mixed results. Fog dispersal is another application, used at airports. Dry ice or propane burners can lift the fog layer by inducing condensation at higher altitudes or encouraging droplet formation and fall. It works best in radiation fog, shallow, low-level, surface-based fog. Cloud seeding is used in many countries: China, Russia, United States, India, United Arab Emirates, France, Thailand, South Africa. Programs vary in scale, from regional weather modification efforts to targeted missions before large events. During the 2008 Beijing Olympics, cloud seeding was used to try and clear skies and prevent rainfall during ceremonies. Some countries use seeding for drought relief, others for snowpack augmentation, to increase water supply, especially in mountainous regions. There are international concerns, ethical debates, and environmental monitoring. Silver iodide, though effective, is monitored for accumulation in soil and water. Its toxicity is low, but still studied. Legal questions have emerged regarding liability and the boundaries of atmospheric ownership. There are also historical precedents. In the 1960s and 1970s, the United States conducted military weather modification under Project Popeye, aimed at increasing rainfall over supply routes. The program was later declassified and criticized. International frameworks exist, such as the ENMOD Convention, the Environmental Modification Convention, which prohibits hostile use of environmental techniques. In warfare, cloud modification remains active, but limited. Most scientists view it as supplementary, not transformative, useful under specific conditions, but not a solution to drought or climate change. The atmosphere is complex. Systems are interlinked. Influencing one region may affect another. Effects may be delayed or dispersed. Clouds respond to pressure, moisture, temperature, particles, but not with certainty. Seeding increases probabilities. It does not guarantee outcomes. It is an effort to nudge nature. Not cont. Roll it. A form of suggestion. Whispered into a system that may or may not respond. Clouds attract not only from the ground, but from above. Satellites orbit Earth, equipped with sensors, optical, infrared, microwave. They collect data continuously, quietly, in loops around the planet. There are two main satellite types used for cloud observation. The first is the geostationary satellite. It orbits at approximately 35,786 kilometers above the equator. At this altitude, it moves at the same rate as Earth's rotation, so it stays fixed over one location. It observes the same region all day and night. Examples include GOES, Geostationary Operational Environmental Satellite, United States; Himawari, Japan; Meteosat, Europe; INSAT, India. Geostationary satellites provide images every 5 to 15 minutes. Useful for monitoring storms, cloud development, and atmospheric motion. They use instruments like ABI, Advanced Baseline Imager. It observes invisible, infrared, and near-infrared channels. Each channel detects a different aspect: cloud height, cloud temperature, moisture content, surface reflection. Visible channels detect reflected sunlight. Useful during daytime. Infrared channels detect emitted radiation. Useful both day and night. They estimate cloud top temperature, which helps infer altitude. The second type is the polar orbiting satellite. It travels at lower altitudes, around 850 kilometers, crosses from pole to pole, covers the entire globe in multiple passes per day. Examples include NOAA Series, US; SWAMI NPP; METOP; Aqua and Terra, NASA. These satellites carry instruments such as MODIS, Moderate Resolution Imaging Spectroradiometer. On board Aqua and Terra, it measures 36 spectral bands, provides data on cloud optical thickness, cloud droplet size, cloud phase, liquid or ice, cloud cover percentage, cirrus clouds, and the Earth's radiant energy system. It measures Earth's radiation budget. How much energy is absorbed? How much is reflected? Clouds are the primary variable. CALIPSO uses LiDAR, light detection and ranging. It sends laser pulses toward Earth, measures how light is scattered by particles, generates vertical profiles of clouds, shows layer thickness, multiple cloud levels, and aerosol cloud interaction. Microwave sensors penetrate clouds. They estimate precipitation, even under dense cloud cover. These instruments are useful for tropical storm monitoring and estimating rainfall rates. Satellites provide data that is both broad and precise. They reveal patterns invisible from the ground. Global circulation, jet stream influence, cloud deck formation over oceans, polar vortex behavior. They also detect cloud trends over time, changes in high cloud cover, shifts in storm frequency, variations in cloud altitude. This data is used in climate models, numerical weather prediction, aviation routing, environmental research. From space, clouds form shifting textures, bands, swirls, fronts, plumes. Cumulonimbus clouds appear as high, cold-topped towers, often surrounded by anvil shapes. Cyclones are visible as spirals, with dense central overcast. Stratus layers appear smooth, reflective, covering oceans in grids and sheets. Cirrus clouds appear thin, streamed out by high winds, almost transparent, but still measurable. Satellites also track cloud shadows, cloud movement, cloud edges, ice content. Some missions focus solely on clouds. Like CloudSat, it uses radar to detect cloud structure in fine detail. Vertical profiles, layering, internal motion. These observations improve weather forecasts, storm warnings, climate projections. They also help validate models and test assumptions. Clouds are not static from orbit. They move, expand, fade. Their boundaries are soft, their forms constantly shifting. From above, they are neither small nor decorative. They are major systems, carriers of moisture, reflectors of light, insulators of heat. They are not observed as shapes, but as values: brightness, temperature, albedo, emissivity, cloud top pressure. Each frame of data is converted into numbers, into maps, into prediction. There is no emotion in satellite data, only measurement and trend. But through this data, we see the atmosphere breathe. We see its patterns, its delays, its rhythms. Clouds are part of that rhythm, observed from thousands of kilometers away. In infrared and silent light, clouds affect aviation in multiple ways. They influence flight paths, visibility, turbulence, icing conditions, and overall safety. Pilots are trained to identify cloud types. Each one has associated risks and operational considerations. The most basic effect is on visibility. Low clouds reduce the distance a pilot can see. This is critical during takeoff and landing, especially in instrument meteorological conditions, IMC, where visual flight is not possible. Stratus and fog are common contributors. Regulations define minimum ceiling and visibility. These determine whether a flight may proceed under Visual Flight Rules, VFR, or must follow Instrument Flight Rules, IFR. Cloud ceilings are measured in feet above ground level and reported in METAR codes, a standard aviation weather format. For example, BKN 020 equals broken clouds at 2,000 feet. OVC 008 equals overcast at 800 feet. Pilots also assess cloud tops Climbing above certain cloud layers can result in smoother air or access to visual conditions. Flight plans may include altitude changes to avoid or cross through specific cloud types. Cumulonimbus clouds are avoided whenever possible. They produce turbulence, wind shear, lightning, heavy rain, hail, and occasionally tornadoes. The updrafts and downdrafts inside cumulonimbus can exceed 6,000 feet per minute, strong enough to destabilize even large commercial aircraft. Modern aircraft are equipped with weather radar. It detects precipitation intensity, not cloud type, but heavy returns indicate storm cause. Pilots steer around them, maintaining lateral separation, usually 20 nautical miles or more. Turbulence is common in and near clouds, especially where different air masses meet, at the edges of frontal zones, or near mountains. This is called mountain wave turbulence. It may be invisible, but predictable. Stratocumulus and altocumulus lenticularis can indicate strong wave activity. Pilots report turbulence using the PIIP system. Pilot reports. They describe turbulence as light, moderate, or severe. Cloud layers are often included in these reports. To aid other flights, icing is a major concern in clouds containing supercooled water droplets. These are liquid droplets below 0 degrees C. They freeze upon contact with aircraft surfaces, especially wings, propellers, and engine inlets. Cloud types associated with icing include stratocumulus, altostratus, cumulus, cumulonimbus. Icing reduces lift, increases drag, can disrupt instrumentation, and lead to performance loss. Anti-icing and de-icing systems include bleed air heating, electrically heated surfaces, de-icing boots, chemical sprays. Regulations restrict flight into known or forecast severe icing, especially for non-equipped aircraft. Clear air turbulence, CAT, occurs outside visible cloud, but can still be associated with jet streams and high-level cirrus. It is unpredictable, but certain cloud patterns, like cirrus uncinus or streaky formations, can suggest its presence. Clouds also affect wake turbulence. Aircraft flying through moist air may leave vortex trails visible in condensation, especially at lower altitudes. This visual confirmation can aid spacing. Training simulators include cloud models to prepare pilots for low visibility conditions. Instrument landing systems, ILS, help guide aircraft through cloud layers based on radio signals and glide slope indicators. Air traffic control, ATC, uses cloud data to assist routing, especially during convective weather events. Flights may be rerouted hundreds of miles to avoid clusters of storms. Meteorologists issue SIGMETs, significant meteorological information alerts. These include severe turbulence, icing, volcanic ash, and cumulonimbus. Commercial aviation uses forecasts from agencies like National Weather Service, NWS, Aviation Weather Center, AWC, World Area Forecast Centers, WAFC. They model cloud cover, top height, movement, and potential hazards. These forecasts feed into flight planning systems and airline dispatch centers. Clouds affect fuel consumption, flight duration, comfort, and risk. They are not obstacles. They are environmental conditions. Assessed, avoided, or endured. Not every cloud contains danger, but each one has structure, moisture, and motion. Understanding them is essential to safe flight. From takeoff to cruise to descent, they are part of the atmosphere. Dynamic, variable, observed. From cockpit windows, from radar screens, and from space. Clouds are not only visual, they are operational and always present. Before scientific classification, clouds were observed, described, named, imagined, not with instruments, but with language, metaphor, and belief. Ancient cultures viewed clouds as more than vapor. They were signs, messages, beings, or borders. In Greek mythology, clouds were linked to the gods. Zeus was the cloud gatherer. Nephil was a cloud nymph. The heavens were divided by mist and atmosphere. Mount Olympus stood above the clouds, the mortal world below. In Hindu texts, clouds are connected to Indra, god of rain and storms. Clouds carried the waters of the heavens. The elephant Airavata was said to create them by drawing water from the oceans and spraying it into the sky. In Norse cosmology, clouds were not often central, but mist and fog signaled transitions between realms. The space between worlds was veiled. Asgard was reached by the Bifrost Bridge, often imagined arched across clouds. Chinese tradition viewed clouds as auspicious symbols. They represented balance and transformation. Cloud forms appeared in art, scrolls, architecture, as swirling patterns. Taoist texts describe the universe as a flux. Clouds were part of the changing sky, impermanent, yet meaningful. In Mesoamerican cultures, clouds were associated with fertility. Rain deities controlled them. The Aztecs offered rituals to Tlaloc. Clouds were tied to mountain spirits, who released or withheld moisture. Early weather observation was descriptive. No measurements, only patterns. Shepherds and sailors watched the sky. Red sky at night, mackerel skies, mare's tails. These were phrases, not formulas. The Bible includes multiple cloud references. Clouds are used as metaphors for mystery, obscurity, divine presence. A pillar of cloud led the Israelites. God spoke from clouds. They marked thresholds. In Islamic tradition, clouds are signs, part of Allah's creation, mentioned as evidence of divine order, carriers of rain and mercy. Clouds in Buddhist texts symbolize illusion. They obscure clarity, drift through the mind, appear and vanish, without form or weight. Meditation likens thoughts to clouds, passing, changing. Early scientific references to clouds were observational. Aristotle described weather in Meteorologica. He proposed ideas about evaporation and condensation, but lacked tools for measurement. The Renaissance brought drawings, sketches of skies, cloudscapes in art. Leonardo da Vinci studied atmosphere and optics. He noted light scattering, but did not create a classification. Clouds remained poetic. The shift to structured observation began in the late 1700s, when temperature and pressure were measured, but cloud types were still not standardized. Luke Howard, in 1802, proposed a Latin-based system, using cumulus, stratus, cirrus, and nimbus. He was influenced by Linnean taxonomy, applying biological classification to the sky. His work gained recognition. It was embraced by Goethe. The poet wrote verses inspired by Howard's names, merging science and metaphor. Howard's system was clear, modular, adaptable. It described the observed, without narrative. By the mid-1800s, meteorology began to formalize. Barometers, thermometers, observatories, cloud descriptions were included in ship logs, weather records, military planning. The idea of standardization spread. By the late 19th century, the International Meteorological Organization began work on a global cloud atlas, published in 1896. It included photographs, descriptions, Latin names, and classification rules. From mythology to measurement, clouds moved from symbol to subject, from divine veil to vapor profile. Yet even now, their visual presence continues to invite metaphor. Despite instruments, despite categories, they remain part of how humans express mood. Still painted, still written, still photographed, but their classification is fixed. Shape, altitude, structure, nothing poetic, only pattern. Clouds are made of water, but not pure water. Each droplet contains trace substances, dissolved gases, microscopic particles, chemical ions. The result is a dilute solution, suspended in air. Cloud chemistry begins with the droplet itself. Each droplet forms around a nucleus. This nucleus is not water. It is a solid particle, called a cloud condensation nucleus, CCN. Examples include dust, sea salt, soot, sulfate, pollen, industrial particles. Without a nucleus, water vapor cannot condense easily. Nucleation lowers the energy barrier, initiates droplet formation. Once formed, droplets are extremely small, ranging from 2 to 50 micrometers in diameter. Each droplet has a high surface area to volume ratio. This increases interaction with the surrounding air. Cloud droplets absorb gases from the atmosphere. This includes carbon dioxide, CO2, sulfur dioxide, SO2, nitrogen oxides, NO and NO2, ammonia, NH3, and ozone, O3. These gases dissolve into the water. They form weak acids or bases. For example, CO2 dissolves to form carbonic acid, H2CO3. SO2 forms sulfurous acid, H2SO3. NO2 forms nitric acid, HNO3. NH3 forms ammonium hydroxide, NH4OH. The result is a slightly acidic solution. Normal cloud water has a pH between 4 and 6. Rainwater is naturally acidic due to carbon dioxide alone. When pollution levels are higher, more sulfur and nitrogen oxides enter the droplets. This lowers the pH further, resulting in acid rain. Acid rain is defined as precipitation with a pH below 5.6. It affects soil, water bodies, plant tissue, and man-made structures, especially those made of limestone or marble. Acid rain does not burn skin, but it disrupts ecosystems. It leaches aluminium from soils, reduces calcium in aquatic environments, affects insect and fish populations, and lowers forest resilience. Cloud water acidity depends on many factors: emission sources, atmospheric mixing, temperature, droplet lifetime, and chemical interactions within the cloud. Cloud chemistry is also influenced by aerosols, fine particles suspended in the atmosphere. They affect droplet number, droplet size, cloud brightness, and precipitation likelihood. Aerosol cloud interactions include the Toumet effect. More aerosols lead to more smaller droplets. Cloud becomes more reflective, less likely to rain. The Albrecht effect. Smaller droplets extend cloud lifetime, reduce evaporation, affect radiation balance. These processes are complex, non-linear, still under active research. Cloud chemistry also plays a role in oxidation reactions. Inside the droplet, dissolved ozone reacts with other chemicals, converting sulfur dioxide to sulfate, nitrite to nitrate, and forming secondary aerosols. These return to the air when droplets evaporate. In the upper troposphere, ice clouds have different chemistry: less water, lower temperatures. Gas exchange continues, but slower, limited by surface area and temperature. In marine environments, sea salt is a common nucleus. It introduces sodium, chloride, and magnesium. These affect pH buffering and scavenging of acids. In continental areas, dust and soot dominate. These particles may contain metals, such as iron, copper, zinc, which can catalyze redox reactions in the droplet. Clouds are chemical reactors, distributed over large volumes. Thin, but widespread, they process air, filter gases, convert compounds, then release them as rain, or return them to the atmosphere. Measurements are taken with aircraft, balloon probes, cloud water collectors on mountaintops, and ground-based monitoring stations. Samples are analyzed for pH, conductivity, iron concentrations, trace metals, organic compounds, cloud chemistry effects, air quality, climate feedbacks, ecosystem health, agricultural productivity, and human infrastructure. But most cloud water evaporates, leaves behind only memory and data. Its chemistry is recorded, not remembered, titrated, not imagined, measured in milligrams per liter, micromoles, parts per billion, small quantities, big implications, invisible processes, occurring in silence, above roads, forests, cities, and oceans. Clouds are a major source of uncertainty in climate modeling. They influence the Earth's energy balance. They reflect solar radiation. They trap outgoing infrared radiation. They are variable in space and time, difficult to measure precisely, difficult to predict. Climate models simulate the Earth systems, atmosphere, oceans, land, ice. They use mathematical equations based on physical laws to project future conditions. Clouds are included in these models, but with limitations. Most models use parameterization. This means cloud behavior is simplified, described statistically, rather than resolved directly. This is necessary because cloud processes occur at small scales, too small for global models to compute in detail. Droplet formation, turbulence, microphysics. These are handled indirectly. Different models use different assumptions about how clouds form, how they evolve, and how they interact with radiation. This results in differences between model outputs, especially in climate sensitivity, the measure of how much Earth's temperature will increase. If atmospheric carbon dioxide doubles, some models predict 2 degrees Celsius. Others predict 4 or more. Much of the variation comes from cloud-related feedbacks. There are 2 main feedback types. Shortwave cloud feedback affects reflected sunlight. If warming reduces low cloud cover, more sunlight is absorbed. The planet warms more. Longwave cloud feedback affects outgoing radiation. High clouds trap heat. If they become more widespread or rise higher, they increase warming. The net effect of cloud feedbacks is still debated. Some regions show positive feedback, others negative. Global averages are uncertain. Satellite observations help refine models. They provide data on cloud top height, optical thickness, cloud fraction, water path, ice content. Instruments like MODIS and Ceres track these variables over time, allowing model outputs to be tested, compared, adjusted. Despite this, cloud behavior remains the largest contributor to uncertainty in radiative forcing estimates. Radiative forcing is the change in energy balance caused by greenhouse gases, aerosols, and cloud changes. Low clouds, especially marine stratocumulus, have a strong cooling effect. They cover vast ocean areas. Small changes in their covering can affect global temperature projections. High clouds, such as cirrus, tend to warm the atmosphere, but their formation and persistence are sensitive to humidity, temperature, and aerosols. Models so attempt to simulate convective clouds associated with tropical systems. These include cumulus and cumulonimbus. They transport heat vertically, release latent heat, and affect circulation patterns. Convective parameterization is another challenge. Models estimate upward motion, moisture condensation, precipitation rates based on bulk properties, not individual clouds. Cloud-aerosol interactions add more complexity. Increased aerosols may lead to more but smaller droplets. This affects albedo, precipitation onset, cloud lifetime, and cloud height. These effects are called indirect aerosol effects. They are included in some models, omitted in others, assumed differently across platforms. Global climate models, GCMs, and Earth system models, ESMs, continue to evolve. They include more cloud processes, higher spatial resolution, more detailed cloud microphysics. But trade-offs remain. Finer resolution increases computational cost. Simplification reduces realism. Cloud feedbacks dominate uncertainty. In the range of climate projections used by the Intergovernmental Panel on Climate Change, IPCC, efforts to reduce this uncertainty include cloud-resolving models, CRMs, largely simulations, LES, high-resolution regional models, machine learning techniques, improved satellite calibration. Despite these, clouds remain a central unknown in both near-term weather and long-term climate. They are dynamic, multiphase, multiscale, visible, but complex, a layer of moisture, reflecting sunlight and holding heat in patterns we still struggle to fully describe. Some clouds are uncommon. They do not form under ordinary conditions. They require specific environments, precise combinations of moisture, temperature, and wind. These are categorized as rare or unusual cloud types. They are not separate genera, but special forms, observed infrequently, recorded under strict criteria. Lenticular clouds are stationary, lens-shaped clouds. They form near mountains, in stable air, when wind flows over a ridge or peak. Moist air is forced upward. It cools, condenses, forms a smooth, layered cloud. Lenticular clouds are often aligned perpendicular to the wind. They appear as stacked disks, isolated, symmetrical. Despite high winds, they remain fixed in place. They indicate mountain wave activity and potential turbulence. Noctilucent clouds form much higher, in the mesosphere, at altitudes between 76 and 85 kilometers. They are the highest clouds in Earth's atmosphere, made of ice crystals, formed on dust particles, possibly from meteors. They occur in polar regions during summer, when the mesosphere is coldest. They are only visible at twilight, when the sun is below the horizon, but still illuminates the high atmosphere. Noctilucent clouds appear pale blue or silver, thin, wavy. They do not affect weather. They are indicators of upper atmospheric conditions. Polar stratospheric clouds, PSCs, form in the stratosphere between 15 and 25 kilometers altitude, also known as nacreous clouds. They occur in polar winters, when temperatures drop below -78 degrees C. They consist of nitric acid and water, or ice particles. Type IPSCs are composed of nitric acid trihydrate. Type IIPSCs are water ice-based. They appear iridescent, with mother-of-pearl colors. Due to diffraction, PSCs are linked to ozone depletion. They provide surfaces for chemical reactions that release chlorine and bromine, which then destroy ozone molecules, particularly in the Antarctic. Undulatus asperatus is a relatively new classification, added to the International Cloud Atlas in 2017. It describes clouds with chaotic wave-like patterns, resembling a rough sea surface. Seen from below, these clouds are mid-level, often altostratus or stratocumulus, but with disturbed bases, caused by atmospheric instability and wind shear. They do not always produce precipitation, but they indicate dynamic airflow. Mammatocumulus or mammatus clouds have pouch-like protrusions hanging from the base of larger cloud masses, common under cumulonimbus anvils. They form when sinking air contains ice or liquid and descends into drier layers. Their structure depends on temperature gradients and microphysical properties. They are associated with severe storms, but not directly hazardous. Fall-streak holes are circular gaps in mid-level clouds, also called hole-punch clouds. They occur when supercooled water rapidly freezes, usually triggered by an aircraft passing through. The ice crystals grow. Droplets evaporate, leaving a hole. These holes are temporary and may be surrounded by thin, diffuse cloud trails. Glories are optical phenomena, not clouds themselves, but seen near cloud surfaces. They appear as concentric rings of colored light around the shadow of an observer, usually seen from aircraft. When flying above clouds, they occur due to backscattering of light B. Why cloud droplets? Virga and precipitatio describe precipitation behavior. Virga is rain or snow that evaporates before reaching the ground. Precipitatio reaches the surface. Both are visible from above or below, as streaks beneath the cloud base. Kelvin-Helmholtz waves are rare, but distinctive. They form as cresting, curled shapes, like ocean waves, caused by velocity differences between air layers. They are short-lived, delicate indicators of shear. These formations are classified based on observation, not mythology. Each one obeys physical laws, defined by altitude, particle content, and motion. They do not persist. They appear briefly, then disperse. Records are kept in the International Cloud Atlas, with standardized imagery and detailed criteria. Though unusual, these clouds are not supernatural. They are atmospheric structures with specific causes and measurable properties. They are part of the system, not outside it. Recognized, catalogued, occasionally photographed, then gone. Clouds are not unique to Earth. They are observed on other planets and moons, each shaped by different atmospheres, different temperatures, different chemicals. On Venus, clouds dominate the sky. The planet is covered by a thick global cloud layer, extending from 45 to 70 kilometers above the surface. The clouds are made primarily of sulfuric acid droplets, formed from volcanic sulfur dioxide and water vapor, under intense solar radiation. The result is high albedo, reflecting most incoming sunlight, but also trapping heat, contributing to extreme surface temperatures, over 460 degrees C. The atmosphere of Venus rotates faster than the surface, a phenomenon known as superrotation. It causes the cloud layers to move rapidly, observed by spacecraft like Akatsuki and Venus Express. On Mars, clouds are thinner and less frequent. They form from water ice crystals or carbon dioxide ice, also known as dry ice. They occur near the equator in the afternoon or near the poles during seasonal changes. Mars has cirrus-like clouds, thin and wispy, observed from orbit and from rovers. Like Curiosity and Perseverance, they form at high altitudes, 20 to 40 kilometers above the surface, moving with the wind, sometimes forming wave patterns. Jupiter has a massive atmosphere, composed mostly of hydrogen and helium. Clouds form in layers, at different depths, with different compositions. The highest clouds are ammonia ice. Below that are ammonium hydrosulfide. Deeper still, water clouds may exist. The bands seen on Jupiter are large-scale cloud systems, moved by jet streams. Each band rotates in an opposite direction, creating turbulence and storms, like the Great Red Spot, a massive high-pressure system persisting for over 300 years. Saturn has a similar structure, with layered cloud decks, ammonia at the top, water vapor at the bottom. Clouds are influenced by strong winds, some exceeding 1,800 kilometers per hour. Storm systems on Saturn include large ovals, long-lasting vortices, and periodic global storms, occurring approximately every 30 Earth years. Uranus and Neptune have colder atmospheres, composed mainly of hydrogen, helium, and methane. Methane gives them a blue color. Clouds are faint, made of methane ice and possibly hydrogen sulfide. Neptune shows more visible weather, including fast-moving storms and bright, high-altitude clouds, captured by Voyager 2 and later telescopes. Titan, Saturn's largest moon, has a thick atmosphere, denser than Earth's, made mostly of nitrogen, with methane and hydrocarbons. Clouds on Titan form in the methane cycle, similar to Earth's water cycle. Methane evaporates, condenses, and rains, forming cloud systems near the poles and equator, depending on the season. Triton, Neptune's largest moon, has a thin nitrogen atmosphere. It shows transparent clouds of condensed nitrogen or methane, barely visible. Pluto, though small, has a complex atmosphere, observed by New Horizons. It contains haze layers, possibly formed by photochemical reactions. Not true clouds, but atmospheric stratification. In exoplanet studies, clouds are modeled using infrared spectra. Planets with hot atmospheres may have clouds of silicates, iron vapor, metal oxides. These materials condense at high temperatures, forming clouds in gas, giants orbiting close to their stars. Called hot Jupiters, cloud detection in exoplanets is indirect, based on light absorption, scattering, and reflected brightness, not direct imaging. Across all bodies, cloud formation depends on atmospheric composition, pressure, temperature, gravity, solar radiation, available condensation nuclei. The physics remains consistent. Condensation, saturation, cooling, but the chemistry changes. Clouds can form from water, ammonia, methane, sulfuric acid, carbon dioxide, sodium sulfide, silicate vapor, matter, LS. Each produces different textures, different opacities, different interactions with light. Planetary clouds are studied with telescopic imaging, spectroscopy, atmospheric modeling, spacecraft observations. Understanding them helps interpret climates, circulation, surface conditions, and planetary evolution. Clouds are not earthbound. They are atmospheric expressions, emerging wherever conditions allow, inevitable in any thick enough atmosphere. Their shapes vary, but their principles remain. Phase chain, condensation, suspension, across worlds. In vapor, cloud research continues. In laboratories, in orbit, on mountaintops, and in code. New technologies improve observation, measurement, modeling, and understanding. The study of clouds integrates atmospheric physics, chemistry, fluid dynamics, remote sensing, and computational modeling. Several next-generation satellites are focused on cloud dynamics. EarthCare Earth Clouds, Aerosols and Radiation Explorer, a joint mission by ESA and JAXA, launched to measure interactions between clouds, aerosols, and radiation. It carries an advanced LiDAR, radar, and multispectral imager. It provides vertical profiles, cloud base, cloud top, optical properties, and microphysical parameters. PACE Plankton Aerosol Cloud Ocean Ecosystem Mission, NASA, designed to observe aerosols and clouds over oceans, and link cloud development to biological activity, including marine aerosols from phytoplankton blooms. GeoXO, Geostationary Extended Observations, planned by NOAA, a future system replacing GOES satellites. It will provide higher resolution imagery, more frequent updates, and expanded spectral ranges. CubeSats and SmallSats provide targeted measurements at lower cost, with higher revisit rates. Examples include RainCube radar and CloudCube cloud reflectance. Beyond observation, cloud research uses AI and machine learning. These tools identify patterns in large datasets, classify cloud types from satellite images, detect changes over time, and assist in short-term forecasts. Neural networks process radiance data and extract cloud properties, such as cloud mask, phase, height, and water path. AI improves nowcasting, providing minute-to-minute cloud motion predictions. Useful in aviation, solar energy management, and outdoor event safety. High-resolution cloud-resolving models, CRMs, simulate individual clouds. At grid scales below 1 kilometer, they resolve convection, microphysics, entrainment, precipitation. These models require large computing power, but provide more realistic simulations, especially for convective cloud systems. Large eddy simulation, LES, models simulate turbulence at scales of tens to hundreds of meters, used to study cloud-top mixing, boundary layer clouds, and radiative transfer. Laboratory experiments also contribute. Cloud chambers recreate cloud conditions under controlled pressure, temperature, and humidity. Droplet formation is observed, nucleation measured, aerosol interaction tested. Examples include the Cloud experiment at CERN, studying cosmic rays and their role in aerosol formation, linking atmospheric chemistry with high-energy particles. The Pi Chamber, USA, a portable cloud simulator used to study droplet coalescence and precipitation onset. Airborne campaigns continue, using aircraft to fly through clouds, collect in situ measurements of droplets, crystals, and aerosols. Examples include NASA's ATTIX and Oracle's missions, NOAA's Hurricane Hunter operations, EUREC-4A, Europe-Caribbean Observational Campaign. Cloud droplets are measured by optical array probes, LiDAR systems, radar reflectivity, and in situ impactors. Balloon-borne instruments collect vertical profiles, often in remote areas, providing temperature, humidity, and cloud water content. Data assimilation systems combine satellite and in situ data, feeding real-time observations into numerical weather models to adjust initial conditions and improve forecast accuracy. Cloud microphysics is an ongoing focus, including the role of giant nuclei, ice multiplication, drop breakup, and freezing behavior. Researchers continue to refine autoconversion rates, droplets to raindrops, collision coalescence efficiency, evaporation rates, ice crystal habit formation. Clouds remain a central question in climate sensitivity, in storm development, in hydrological cycles, and in energy forecasting. Despite centuries of observation and decades of measurement, clouds are not fully understood. They are studied at multiple scales, from molecular diffusion to planetary circulation, from vapor chemistry to radiative transfer. Research continues with better tools, better models, and more data. Clouds are the interface between sky and system. They connect solar input to terrestrial outcomes, not passive, but dynamic, not random, but structured, red, still forming, still shifting, still studied. Clouds influence human perception, emotion, attention, and memory. They affect physiology indirectly and cognition subtly. This has been studied in psychology, environmental science, and behavioral research. Light diffusion through clouds alters illuminance. Cloudy skies reduce luminance contrast. This lowers alertness, increases melatonin production, and may slow response times. Overcast conditions are associated with a reduced visual clarity, lower color saturation, fewer shadows, flat light. These changes influence mood. In some individuals, prolonged low light exposure leads to fatigue, sadness, sleep disruption. This is known as seasonal affective disorder, SAD. Common in high latitude regions. Less sunlight in winter. More cloud cover. Reduced ultraviolet exposure. Disrupts circadian rhythm. Light therapy is a treatment. It uses artificial sunlight to simulate brightness and suppress melatonin. Cloud types correlate with mood perception. Cumulus clouds are often seen as pleasant, fluffy, white, scattered. Nimbostratus clouds suggest gloom. Gray, thick, associated with prolonged rain. Cirrus clouds are neutral, seen as wispy, distant, aesthetic. Clouds affect thermal comfort by reducing solar heating, shading surfaces, altering wind patterns. People report higher comfort on partly cloudy days compared to clear, hot ones. In architecture and urban design, cloud cover impacts. Natural lighting indoors. Window orientation. HVAC loads. Solar panel efficiency. Cloud studies are used in bioclimatic architecture to model skylight availability and plan passive cooling systems. Clouds impact outdoor behavior. Studies show that cloudy days reduce pedestrian activity, park visitation, UV exposure, time spent outdoors, but increase museum attendance, screen time, indoor purchases. Cloud imagery is used in advertising and media to convey tone. Cumulus optimism. Stratus equals melancholy. Sun rays breaking through clouds equals hope. Visual artists have studied cloud forms since antiquity. In Chinese landscape painting, clouds represent transition. In European oil painting, clouds show divine presence. In romantic art, they symbolize the sublime. In photography, clouds add depth and contrast. In literature, clouds are metaphors for confusion, uncertainty, dreams, or transcendence. In religion, clouds appear in texts as symbols of heaven, of concealment, of revelation. In music, clouds are used in lyrics to describe longing, distance, or drifting. Scientific cloud classification has influenced visual design, including weather icons, flight displays, simulation environments, and digital art. Cloud computing metaphorically extends this. The invisible layer, above human perception, carrying unseen systems. In education, clouds help explain cycles. used in primary school to illustrate water vapor and weather dynamics. Children draw them early. Adults watch them idly. The forms change, but remain familiar. Clouds are ambiguous, non-permanent, continuously transforming. Humans often assign emotion to their patterns. This is pareidolia, the tendency to see faces or meaning in random stimuli. Clouds are common subjects. Faces, animals, stories. Their fluidity triggers imagination, but also reflection and calm. Watching clouds is studied as a form of mindfulness. It induces relaxation, slows breathing, reduces mental noise, called cloud meditation or sky gazing. In some practices, clouds anchor attention without requiring analysis. They shift slowly, without urgency. The Cloud Appreciation Society was founded in 2005. It has thousands of members from over 100 countries, dedicated to photographing, classifying, and enjoying clouds. They maintain an archive, categorize cloud sightings, celebrate new formations. Clouds are used in therapy to stimulate memory or represent emotion. Children are taught to breathe like a cloud, slowly, softly, changing shape with thought. Though not tangible, clouds touch perception. They pass above cities and oceans without noise, silent, transient, unconcerned, yet quietly meaningful. Clouds are part of Earth's energy balance. They reflect sunlight. They trap heat. They regulate temperature. They connect surface and sky. Their behavior is not constant, but patterns exist, influenced by latitude, season, ocean currents, and altitude. High clouds like cirrus are cold. They trap long-wave radiation, warming the surface. They have a net warming effect. Low clouds like stratus are dense. They reflect incoming solar radiation, cooling the surface. They have a net cooling effect. Cloud albedo is the fraction of sunlight clouds reflect. Thicker clouds reflect more. Thin clouds reflect less. Cloud cover varies globally. On average, about 67% of Earth is covered by clouds at any moment. CL. OOD feedback is uncertain. Warming may increase water vapor, which increases cloud formation. But the type and altitude matter. Some models show increased high clouds, which trap heat. Others predict more low clouds, which reflect light. The net result is still being studied. Cloud feedback remains the largest source of uncertainty in climate projections. Cloud radiative forcing quantifies this. It is measured in watts per square meter. Positive forcing equals warming. Negative forcing equals cooling. Satellites like MODIS and Ceres observe these effects. They record cloud height, thickness, and optical depth, and track changes over time. Clouds also affect precipitation. They form raindrops, snowflakes, and hail. They determine where water falls. And when they shape rivers, fill aquifers, sustain vegetation, they affect solar energy systems by blocking or diffusing light. Engineers account for cloud behavior in panel orientation, forecasting, and energy grids. Clouds scatter radio waves. They can degrade signals or reflect them. They influence aviation, telecommunication, and satellite visibility. They mark turbulence, storm boundaries, jet streams. Cloud data is archived by NOAA, by UMETSAT, by the World Meteorological Organization. Clouds are input in every global circulation model, GCM, updated regularly, adjusted with observation, compared against forecast. Yet they remain elusive. No two clouds are identical. Their shapes are temporary. Their lifespans vary. From seconds to hours, they appear in patterns, then vanish. Clouds are used in long-term climate monitoring, tracking trends in coverage, thickness, altitude, and cloud top temperature. This informs discussions about energy balance, surface warming, and precipitation shifts. They are also tracked on other planets, on Mars, on Venus, on Jupiter. But Earth's clouds are unique in scale and complexity. They connect all parts of the water cycle: evaporation, condensation, precipitation, runoff. They shape ecosystems, regulate temperature, and fill reservoirs. They also frame human perception. They mark sunsets. They shadow landscapes. They decorate stillness. They drift. They build. They dissipate. They do not stay. Yet they return. Clouds are ordinary, but essential. They are studied, classified, photographed, predicted. Still, each cloud is temporary, still forming, still vanishing, still part of the system. They remain overhead, quiet, unnoticed, present, a ceiling, a signal, a shield. Nothing more, nothing less. Just clouds. Clouds are changing. Not visibly, not instantly, but measurably. Observed shifts in cloud behavior are linked to warming oceans, expanding deserts, melting poles. Satellite records show a gradual migration of cloud belts toward the poles, away from the equator. This alters rainfall patterns, lengthens drought seasons, and shifts storm paths. The intertropical convergence zone, where trade winds meet, is slowly widening. Clouds form farther apart. Rainfall becomes less predictable. Subtropical dry zones expand. Mid-latitude storm systems shift. Jet streams wander. Blocking highs linger longer. High clouds increase in coverage. Their tops reach higher altitudes. Colder, brighter in infrared, but thinner in mass. Low marine stratocumulus clouds may thin out or break. This would reduce Earth's albedo, allowing more sunlight to reach the surface, warming it further. Cloud feedback is still the greatest uncertainty in climate sensitivity estimates. Some models predict net positive feedback, more warming. Others show slight moderation from increased precipitation and evaporation cycles. New observation methods improve clarity. Geostationary satellites now observe clouds every 5 minutes. High resolution, multispectral, multi-angle, GOES 16, Sentinel-5P, Himawari 8. Together, they map cloud optical depth, microphysics, and lifetime. Machine learning models assist. They process satellite data. They detect subtle cloud trends and improve climate forecasting. Cloud resolving models simulate small-scale interactions, convection, droplet formation, ice crystal behavior. These models run at high computational cost. They require thousands of nodes, hours of simulation time, but improve accuracy. They also inform solar energy planning, agricultural forecasting, disaster readiness. Cloud data contributes to flood prediction, heatwave warnings, aviation safety, air quality models. Cirrus clouds now appear where they did not 50 years ago. Arctic cloud decks persist longer. Monsoon clouds shift timing. El Niño patterns alter cloud masses over oceans. These patterns are not visible day by day, but they accumulate like sediment, like erosion, slow and steady. Cloud types still follow physics. Warm arises, moisture condenses, ice crystals grow, but the boundaries shift and the rhythms change. New instruments measure cloud top brightness in infrared wavelengths. Others measure microwave scattering to estimate droplet size. Airborne missions, like NASA's Activate, collect in situ data, flying through cloud layers, measuring humidity, particles, and temperature gradients. Their goal is precision, to reduce error bars, to make models match observation. Still, uncertainty remains. Clouds are chaotic, fractal in nature, influenced by small eddies, dust particles, and radiation balances across hundreds of kilometers. One cloud can contain billions of droplets. Each droplet's path depends on wind, solar flux, and microscopic interactions. Clouds are fluid systems, shifting, interacting, adapting. They absorb history. They mirror environment. They respond to warming. Their future is still under study, under watch, under change. Clouds are never still. They are always forming, always fading, never finished. Even when the sky seems empty, vapor is rising, waiting for a shift, a seed, a breath of cooler air. The same principles apply over cities, forests, oceans, ice sheets, deserts. The process repeats. Invisible, patient, evaporation, condensation, coalescence, fall, then again, then again. There is no beginning, no final form, no perfect shape, only movement. Clouds are transition between liquid and gas, between surface and sky, between sunlight and shade. They soften light, they cool soil, they carry water without touching ground. They do not choose their form. The atmosphere shapes them. Temperature defines them. Altitude lifts or flattens them. Wind stretches them. Gravity rounds them. Yet they are not passive. Clouds modify their own surroundings. They trap warmth. They scatter radiation. They cast long shadows that cool the earth. They lift dust, feed storms, shape perception. Some clouds last minutes. Others linger for hours. A few circle the poles for days, without breaking. But none stay. Clouds are always on their way to becoming something else. Rain, mist, ice, nothing. A cumulus over a prairie may have formed from evaporation off a distant sea. Its droplets once touched a glacier, or an animal's breath, or a leaf. Water circulates. So does memory. Held in vapor, released in rain, carried in the wind. You felt it on your skin, on your window, on your thoughts. Clouds do not speak, but they explain. They follow quiet rules, always in motion, always returning, never asking for attention. But they get it. A child looking up, a pilot navigating turbulence, a farmer watching for rain. Clouds are witnesses to volcanoes, to cities, to migrations. They mark seasons, signal change, cover endings. In paintings, poems, dreams, clouds appear. They vanish. They remain.